to image processing. Tonight we're going to talk about the sampling and interpolation processes required for us to manipulate continuous tone images on a computer and also to display out the pictures on a computer. So the basic ideas are very fundamental, and many different discussions have been done about, is the world actually discrete or is it continuous? And in doing so, we'll look at some Fourier descriptions of a particular image function and see that in the proof of the sampling theorem, we can do that very easily by transforming the image into the frequency domain and doing a filtering operation in that particular domain. Let me first stand up and emphasize a few of the topics that that are very crucial and always fundamental in any of the work we do on the computer. One of the basic ideas is that we would only be able to work with a discrete array of numbers. If we have a continuous image function f of xy to start with, there's really no way we can process that in the computer. We could process it in an optical, on an optical bench or with an optical system, but it's impossible to store an infinite number of points in any of the finite memory spaces that we have available now. So what we will typically do is digitize the picture and perhaps store a representation f of ix and jy. So just as in the one-dimensional sampling case, we'll have a two-dimensional sampling theorem, and in fact we could extend it to three-dimensional sampling or four-dimensional as well to show us that we have to have a large number or a given number of discrete points like this so that we could represent the continuous function f of xy. It's sort of startling to look at the sampling theorem, which says that you could represent even a very continuous function by only a discrete set of numbers if you have the sampling sufficiently dense. So sampling will be one fundamental process we'll look at, and we'll look at the two-dimensional sampling theorem as well. The samples would discretize the spatial coordinates of our two-dimensional function. But again, to process it on the computer, if the function values are continuous, there's no way that we could store a continuum of any particular operator. So that we actually have to also quantize the functional values. And the quantization process is very fundamental, and we'll see later in image data compression and communications work, it can be the whole basis of a data compression scheme. So this would give us a discrete set of points, and this would give us discrete tone for those particular points, and we would like to do each of those in an optimum manner, or at least a near optimum manner for imaging. But we'll see that in image processing, the sampling theorem has to be followed, but is usually not followed as precisely as we would have to in signal processing. We can generate aliasing errors that you've probably heard about. If you don't have sampling dense enough, a systematic type errors will be produced, but fortunately we can ignore most of the aliasing errors in images as well, and often use the aliasing errors to even help us recognize some of the image that we're looking at. Okay, but quantization would be the process where we take the continuous tone values and turn those into a discrete set of numbers as well. And there, one of the fundamental questions is how many levels or discrete tones should be represented. And these would be the two steps for getting our data into the computer. So we could go to the computer with these. But if we wanted to take our computer image and display it, we would have to put in another step. The interpolation step to show us how to take the discrete set of numbers that we've generated through the sampling and quantization processes and display these back out so that it would again be a continuous tone representation. And if we've followed the rules as we've gone along, maybe we could make it exactly or very close to the f of xy that we would start with. So this would be how we would go from the computer back into the continuous world. Okay, so we'll actually need to look at three different fundamental processes, and for most of these we at least have some theoretical guidelines that will tell us how to go about these processes. Notice that in this particular two steps of sampling and quantization, we've built a digitizer, or this is what we would normally call an image digitizer. While in the last step, we've built an image display. And we'll see that there are many different solutions to both the image digitization and image display devices. In our course, we'll use just a line printer for doing image display. If we were very concerned about fidelity, we'll see there are many options, including a digital refresh display, a computer output to microfilm device or flying spot scanner devices, plasma panel displays. There's a whole host of these that we could use. All of them do some type of interpolation to take a discrete set of points back into the real world. Okay, so we'll look at these, all three of these steps tonight, and let's start just with the sampling process. The basis for all our theoretical work on sampling is the fundamental sampling theorem. And this was derived by Shannon and Rayleigh and some of the fundamental information theorists, and it's a very non-obvious theorem. But basically it would simply state that that a continuous function could be represented precisely by a set of discrete points one too many there. Okay, what would be the conditions on the sampling theorem? And here I'm assuming that you've probably seen the sampling theorem in one-dimensional signal processing before. And what are the conditions that would make it true? Okay, first let's look at the condition on the type continuous functions that could be represented by the set of discrete points. Only the class of band-limited functions would satisfy this particular theorem. So there are probably some functions, I'm sure there are some functions that are not band-limited type functions. For band-limited, we would, let's first introduce what we mean by that, and then put it down as our condition and see how it would work. So one condition would be that f of xy is band-limited. By that, we simply mean that the Fourier transform of f of xy which is simply for discrete functions an equation of the form I'll use this with the simplest notation. That's our equation for the Fourier transform of f of xy. Notice in the forward transform it has an exponential of minus j. Here it depends not only on the spatial coordinates x and y, but also on two frequency coordinates, u and v. It's a definite integral from minus infinity to infinity in both the x and y directions. And for simplicity, we'll often refer to this simply as capital F of u and v, the two spatial coordinates for that particular function. So cap F of uv is a complex function and is continuous, and by band limited, what we will be saying is that this function will be zero outside some region of the two-dimensional UV space. So our band limited function, if we plotted it in the frequency space of u and v, we should be able to define some rectangle like this that I'll call R, that the f of uv is zero outside that particular rectangle. And it might have function values in here. Typically, might be a big bright spot in the center or something like this. But it would be zero in all these locations. Okay, so one of the conditions we have to put on the sampling theorem is that the function be band limited in terms of being zero outside some rectangle in this particular space. What's another condition that we would have to put on the sampling theorem? Okay, I've got continuous, and now we've made it band limited. So we've sort of, by putting the band limited condition on it, simply said that it can't have too many variations, even in the two-dimensional space. Maybe the next condition would be how many points we have to have. We've said we're going to use a set of discrete points for it. That here I've assumed that capital X and capital Y are constants and I and J are indices. What should the capital X and capital Y be, and what should the indices? How many points should those go over? Okay, let's try to get an idea of those conditions by looking a little bit more at the situation in the frequency domain. Okay, let me skip to another board. Do a little bit more accurate sketch of a function that's band limited to a rectangle. Gee, let me make this a about equal distance rectangle. And in fact, the proof of the sampling theorem, we could almost intuitively derive it just starting from this type analysis. Suppose we have a function that's just defined in this particular portion of the space, and zero outside of it. Then certainly we could do the mathematical trick of making a periodic extension of this particular function. So if I use these as the periodic links in both directions, certainly I could form a periodic function that would have a replica of this one at some other portion where this one is going to be zero, and I could continue these replica spectra indefinitely. all throughout this particular space. Now, the interesting thing about this construction is that certainly my original function is still retained in this particular image, right as the original replica spectrum. But the reason that I would want to make it continuous and periodic, or make it periodic, is simply that I could use a Fourier series representation. We can leave a couple more. Okay. So now by having it a continuous periodic function, I can represent it by a Fourier series, as long as it has a finite or amount of energy in the first replica for that. Because we can represent any periodic function that's square integrable by a Fourier series representation. Let's say I do that, and I call this entire function my periodic extension of the other. This would be f sub p. In the frequency domain, f of uv, or in the space, uv space. If I did this, how would the Fourier series look for representing this particular function? What are the equations of the complex form of a Fourier series? Anyone remember this? Let's see if I remember them. Okay? Let me go over to another board. See how bad my memory is, or how good it is. Okay, I have a periodic function in 2 dimensions. I know that I should be able to then represent my function exactly by a discrete Fourier series. It would only have harmonic terms, right? So I could write that f sub p of uv is equal to a discrete summation, and in the complex form of the series, I would have a coefficient here and different harmonic terms for the complex exponent term. Let's call this c sub ij. And as I remember correctly, in the Fourier series representation, with complex numbers, these would have to go from minus infinity to infinity. Right? If I use the sine-cosine form of the Fourier series, these summations would only go from 0 to infinity. So I would make this for from minus to infinity for the I, and minus infinity to infinity of the j. And then what does the exponential term look like here? First is a plus or minus j. And then I should have some harmonics of some particular fundamental frequency. At this point, let me walk back to the other board and define our periodic interval. Give it a symbol, and we'll use that in this equation. Okay, so now I have to put some symbol down to represent this size in this particular space. Again, this is still the frequency space, the UV space. We could consider this as the origin of the space and going from over symmetrical limits, minus and plus. So if I made this minus capital U over 2 to U over 2 over here, and minus V over 2 to large V over 2 up there, that would give me a particular frequency region for both this variation in spatial frequency and this variation in frequency, right? And now from our Fourier series analysis, remember that we always have integrals that integrate over these limits that multiply a complex sinusoid by our original function. In the first case, we just integrate over these limits to get the average value of this function. And in higher harmonics, we take a sinusoidal modulation, multiply by that function, and integrate it up. Okay, now with this definition of the band-limited region, let's go back and we can write this equation. say I is the subscript in the u direction and j is the subscript in the v direction, then the frequencies involved here should be harmonically related to the fundamental frequency of this particular function. What's the fundamental frequency of it? Is it u or 1 over u? And we might have to think of a time signal example to do this. In a Fourier series of a time signal, what's the fundamental frequency if the period of it is capital T units long? Pardon? Okay, we could use a 2 pi over T if we wanted to talk about it as a fundamental frequency in radians. And, right, since I didn't put a 2 pi in there, we might want to do that. Okay, so it's the reciprocal of the length that we have. So we might have a integer time I from this summation times 2 pi. Let me keep the 2 pi out here. I divided by u. Would it also be j divided by v? So would this give us the harmonic relations required in our Fourier series representation? Doesn't quite look right. What are we missing? It's in the numerator? Okay. Okay, the question is u or 1 over u the fundamental frequency? Now, and we have to think about this in the frequency domain as being equivalent to a time domain, because that's where we're running the periodic extension equations. I'd have to look this up as well. So it's in the numerator. Let me do a one-dimensional example as an analogy. Let's say we have a periodic square wave function. Okay, and this is f of t versus t. So how would we write the Fourier series of f of t? See if I can do this one. Okay. Whoops. Let me make the t the period of it instead of the width of it. Okay, so its period of duration is capital T. What's the fundamental frequency? Is it T or 1 over T? Okay, so in this case, it's 1 over t pretty clearly. What would this be? Is it I over capital T?
The times for t.
Right. Okay. So is that correct for the one-dimensional case? Okay, now the only thing we're doing different in the two-dimensional case is we're starting out in the UV space rather than the others. And our fundamental frequency in the UV space is of width u in one direction and capital V in the other direction. So by this same analogy, shouldn't this be I u over capital U and I and J V over capital V? Pardon?
Two J's up there indicate different.
Right. Okay, let's make this M and N. And that will leave that at I, yes. Okay, so the fundamental frequency is 1 over U in one direction and 1 over V in the other direction. Our index, our harmonic index would be M and N, and this would be a function, the sinusoidal functions of U and V. Is this what the book has? Hope so. Okay, any questions up to here? Or?
That equation is for the equation is for the fundamental frequency, right? Or the one, no, the bottom one. Yeah.
Mm-hmm. Right. The fundamental frequency here was the reciprocal of the time duration. And the same in the two-dimensional case. Okay, the sampling theorem won't work unless I have this part correct. Okay, so we have a Fourier series representation for our periodic function in 2 dimensions. Now, and we have some coefficients C sub mn that would also have to determine. And we can use the Fourier series theory to show us also how to determine C sub mn. So all we would have to do is compute the C sub mn by 1 over our total period, which is in this case, in the two-dimensional case, the product of U and V, and an integral over that fundamental replica T over 2 of our original function. What's the original function? Okay, it would be, in this case, we can make it f of uv or f sub p of uv, right? Because they're exactly the same in that one space. And what type of exponential would we multiply this by? Okay, might use a plus j 2 pi. Would it be the same? Okay, so it's easy for us to figure them out. This would still be m lowercase u over capital U plus n lowercase v over capital V. Okay, and since I know f sub p during that first replica, and this function we know very well as being our complex sinusoid of a continuous argument, in this case u and v, and the discrete values of m and n in the fixed constants of capital U and capital V, I can certainly compute the C sub n m n values for our Fourier series representation. Okay, so now we have periodic function. How could we get back to our original function? And to get an intuition about how to do this, let's move back to the other board and look at the periodic extension function and see how we could get back the original replica